All right, this is the last presentation. Our speaker is Julian Brandner from FAU at Germany, and he's going to be presenting reducing OpenMP to FPGA round trip times with predictive modeling.
Thank you. First, I'm going to get us all on the same page on what OpenMP-to-FPGA target offloading conceptually is and how it works. There are some different projects on how to do it. And the idea is, well, we know OpenMP to GPU offloading, and we want to execute a target region on an FPGA in hardware, utilizing the benefits of FPGAs. So the general concept is in all these different projects to try to do that similar. Let's have a look at a short code snippet. Here we have like a short code with an array called data, and we first initialize it, then we modify it, and then we modify it again. And the first modification happens within a target region, and it's using an additional function called foo. So we want the second modification, the for loop, running on an FPGA in hardware. So normally you do that by having two compile passes, one for the FPGA and one for the CPU. So on the CPU side of things, it's really similar to what we know from GPU offloading. So we don't actually need the target region itself because it has to run on the FPGA. And we can get rid of the pragma. We can get rid of the pragma that way. So we replace the target region with function calls that handle the communication with the FPGA. So we first have to shift the data to the FPGA. Then we have to start and await the computation, and then we get our data back. And well, then we can work with data from there. And normally this is done well with a really classical source-to-source transformation. So we get C source code back, and that you can just compile with your normal OpenMP compiler, and you got your binary. So on the FPGA side of things, we only look at the target regions and the functions that are called by the target regions directly or indirectly, naturally. And well, then we have to turn exactly these code snippets into hardware. And this process is called HLS, high-level synthesis. You translate imperative code, C code, C++ code, whatever, into a hardware description. And the HLS, well, there are different implementations of HLS. The most well-known come from the most well-known hardware vendors, namely Xilinx and Intel. And this step is absolutely critical to the performance of the final system because, well, it decides on how the actual user code is computed in hardware. So the FPGA pipeline for the FPGA compiler pass looks something like that. You take your target regions as snippets, you take everything they need, and you bundle it up together, and then you use HLS to turn it into a so-called IP kernel, IP for intellectual property. That's like a hardware block that computes one target region. And then you take all your hardware blocks and then bunch them up together again into, well, the final product. You have to add infrastructure, like handling the communication with the host device, or handling communication with the FPGA main memory. And you end hopefully up with a so-called bit stream. That's a binary for an FPGA you can program it with. And from there on, well, it depends on your actual use case. You can then program your FPGA with a bit stream and run the host binary somehow connected to this FPGA, and you'll get your execution environment. So where's the problem here? The problem is the HLS. Because if you just take unmodified C code and you pour it into the HLS, you will get poor performance by default. And that's a problem we don't think was addressed previously. HLS, like OpenMP, has pragmas, so-called HLS pragmas, and they are, well, essentially necessary to achieve good performance. If you go without HLS pragmas, you will get a really conservative approach, like conserving hardware resources in the solution. And this will probably not perform well. So these HLS pragmas, they control how C structures like functions, like loops are translated into hardware. And here's an example for here, the for loop. You can use pragma HLS pipeline So the for loop will be, let's say, unrolled into a so-called hardware pipeline, greatly reducing the loop latency. So how does one select the right HLS pragmas? And this is not a trivial problem. You have to balance the amount of hardware resources that you're using and the performance you want to achieve. So a seasoned HLS developer would then go ahead and look at, on the one hand, on like resource estimates that predict how much of the resources of the FPGA are used. And on the other hand, there are performance estimates. So you could balance that out using these estimates, and you'll go on from there. For a not so seasoned HLS developer, or let's say an OpenMP developer who just got into target offloading and just wanted to work, this is not really feasible because especially these performance estimates that are given by HLS tools, well, they are on their own hard to interpret, and you actually have to supply a lot of additional input to even generate them. Like you have to pose assumptions and write them down in a really special notation and something like that. So HLS, an OpenMP developer, would really have to rely on trial and error and just try out a few different things until they would get a good performing heterogeneous system. But this is in most cases not feasible because the full hardware pipeline, like from your target region to the final hardware, can take up days to compute. Like the HLS is 1 minute in itself, that's okay. But the final step, the generation of the bit stream, is in our cases like something between 2 hours and 2 days. It was tedious. So we think the OpenMP developer needs some help here. And this is our approach to do that. Well, as already stated, there are performance estimates that are hard to read, hard to get. But there are area estimates on how much of the FPGA's resources will be used by your target region. And these estimates are really easy to obtain. Like they're just written out by default if you start the HLS. And as already stated, there is a correlation between the area usage and the performance. At least this is what users would suspect. Like if you generate parallel hardware, you need more of it, but you'll get better performance out of it. So our idea was we wanted to check if we can abuse this correlation and use it to predict performance from the area usage. And that would yield us with like a measure to predict the performance of your target regions on the FPGA without actually running any of the full synthesis. It takes up days. And without using any additional input. So this is what we did. We first generated like a large data set from a few OpenMP target offloading benchmarks by inserting random combinations of these HLS pragmas into them. And then we synthesized every sample within that data set. That took some time. Then we first checked if these area estimates are even reliable for OpenMP-to-FPGA target offloading, if they are actually correct, since we then had the final product. And well, then we ran every sample on hardware. We generated the binaries, we generated the bit streams, and we ran the heterogeneous system and measured the performance. And after that, we separated these data sets into two, like a test and a training data, really classical. And then we tried to learn to predict performance from the initially supplied area estimates. So how did we generate samples? Let's have a look at this short code snippet. It's a function and it contains a loop. And we looked at these 3 pragmas from Vivado HLS. Now it's, I think, called Wheatis. Well, this is what our OpenMP-to-FPGA target offloader used, so we stuck with that. And all of these pragmas can't actually break your code. They can't produce wrong results, but they all can increase the degree of parallelism within it at the cost of hardware usage. For example, the unroll programmer here, well, it unrolls the loop, which means in the terms of HLS, it enables multiple iterations to run in parallel. Or the inline programmer, well, it inlines the function upwards, which in the world of HLS means the content of the function can run fully in parallel with the calling function. All of these programmers take additional parameters, so we generated them too at random within the legal bounds according to the specification. So these were our benchmarks. They are all selected because they all react well to the insertion of HLS programmers. You could do, well, arbitrary OpenMP target region code, but if we have code that, well, where programmers doesn't change anything, you would have to collect a lot of more samples to actually get meaningful results. So we took these. There are 3 algorithms from hashing, because hashing on FPGA is somewhat of a classic. And we have odd-even transposition sort is basically a sorting algorithm optimized for FPGAs. Filter is your 2D image convolution, and Mandelbrot is, well, the famous fractal that's a staple in benchmarking parallel systems. So what were our findings? First, we wanted to check if these area estimates that we are about to use are actually correct for OpenMP-to-FPGA target offloading. And how to read this table is, lookup tables, blockram, flip-flop, and digital signal processors are the main resources that an FPGA uses to compute your logic. And these numbers are the Pearson and the Spearman correlation. Pearson correlation is a correlation coefficient by value, and Spearman correlation is a correlation by rank. Meaning, is the predicted best actually the best, or is the predicted worst actually the best? So, for the first 4 benchmarks, the results are surprisingly good. Like a correlation of 1 would be a perfect 1-to-1 correlation, and a correlation of -1 would be a perfect negative correlation. 0 would be no correlation at all. And especially for the users of lookup tables and flip-flops, we get a really high correlation, close to 1, which means we can actually predict how much resources an FPGA and an OpenMP target region will use when executed on the FPGA. If you are wondering, blockram slices are only reported on the cases that used a lot of them, because in our final report, the blockram slices are reported in really big, like 40 kilobyte slices. And well, if you don't use that much, you won't have a correlation. And digital signal processors are mainly used for floating point computations. So they are only used on floating point benchmarks. And that's where we get now. Well, because for the floating point benchmarks, all correlations, even the ones for the digital signal processors, are way lower than on the non-floating point ones. Meaning that if you want to offload a target region that uses a large amount of floating point computations, you probably can't rely on any estimations. And this holds true at least if your OpenMP-to-FPGA offloader uses the classical HLS tools. But all in all, we can predict at least the other ones, and the floating point ones are way harder, but we get still meaningful numbers there, like around 0.6 or something like that. So the next thing we did was, well, we measured the performance of all these samples, and then we checked our initial assumption that there is a correlation between area usage and performance. So we checked that, and we actually got what we expected. These are all negative correlations, meaning more usage of these resources correlates with lower performance. But on the other hand, these numbers are really inconsistent, and they are quite small on average. So you can say that usage of more lookup tables means better performance, but you couldn't use this correlation directly to optimize your code or something like that. Because on most benchmarks, only one of the 2 correlations is significant, and it's fluctuating really heavily. And another interesting side note is for the users of blockram, the correlation is actually the other way around. So on our samples, using more block RAM meant better performance. No, meant worse performance, that way around. So for each of these benchmarks, we had like multiple weak correlations. They are significant, but they are not enough to be used productively. But you can combine multiple weak combinations in one single strong one by using regression models. And that is what we did. We used these three classics of regression in this paper. And the first one is linear regression, which is basically just a linear combination of the four numbers into one single number, which hopefully predicts the final performance. We used decision trees and we used random forest regression, which is just a combination of multiple decision trees, each one trained on a different subset of available data. So let's have a look at the final numbers. Keep in mind, we separated test and training data. So these numbers are produced on a different data set than the training was done on. The linear model, well, it produced better numbers than each of the naive approaches from the two slides before. The linear model predicted the performance better than every single resource on its own, but the numbers are not high enough to be used still, I think. The reason being probably that there is no linear connection between hardware usage and performance. On the other hand, there could be a nonlinear correlation. And well, we found that with the tree and the forest, and especially the forest did really well in predicting the hardware performance from the area usage. Average being 0.9 in Pearson correlation and 0.7 in Spearman correlation. So back to the drawing board, what do we do from there? What can we do with our model from here? So let's say we have our short code snippet and we want to find out how we can optimize it using HLS pragmas. So we would start the HLS, which takes around 1 minute, and then we would start the model, which is basically instant. And we get some generic score number, in this case, something like 0.79. This doesn't tell us that much on its own, but then if we insert HLS pragmas into it and repeat the step and know that this number will correlate with the performance, here, really simple example, we inserted like a pipeline into the first experiment and an unroll pragma into the second. And we get 3 different numbers, and one of them being significantly lower than the other, which indicates that probably this sample will be way faster. Keep in mind, this is a simplification. If you just offload one single for loop, you probably won't get any good performance anyway. So we can actually use this model to predict the performance and to optimize our code. And to sum this all up, we had Pearson and Spearman correlations. High Pearson correlation coefficient means that the regression shows a general trend really well. So if the model tells you that your snippet is really good, it probably is. And maybe even more importantly, the Spearman correlation, which was still pretty high, means that the relation between 2 samples is presented well. So if the model tells you that sample A is way faster than sample B, it probably is. So we can actually use this model to optimize our code, but we should keep in mind that we can only trust the predictions on the other axis. The uses of hardware that we have to keep in mind so we don't overshoot the capabilities of our FPGAs is not reliable if we are using floating point logic. So what do we hope to do from this? Well, until now, you can only use our model to manually optimize your code. But you could also use it to automatically optimize it, because the high Spearman correlation means that like small incremental changes are viable. So a compiler could automatically employ a meta heuristic or something like that to optimize your code. This is where we want to get eventually, that the OpenMP developer doesn't have to think about HLS and what these pragmas are at all, and can just write normal OpenMP code and offload it to an FPGA. So if you're planning anything similar, our samples are available in GitHub. And thank you for your attention.
Thank you, Julian, for the presentation. Any questions?
So thank you for an interesting talk. My name is Saisuke Boku from University of Tsukuba, Japan. So I have a couple of questions. That first, what compiler are you using for your evaluation?
For the creation of the binary or for the HLS?
Yes, binary.
Binary. Well, we tried both. We tried GCC and CLang, like LLVM. For these evaluation, it was LLVM, like the normal OpenMP LLVM current version.
Okay. So that actually is I'm not completely understand about inside of the work, but so I think that most of the performance bottleneck of the FPGA, we are running the practical code, real HPC practical code on the high-end FPGA like Intel Stratix 10. So I think that most of the performance bottleneck of the FPGAs came from the couple of the reasons. One is how it's a well pipeline is a very low initiation interval of the pipeline. The secondly, how we can utilize the spatial parallelism on the maybe some unroll, for example, unroll program makes a spatial parallelism and also hides a memory latency. And sadly, the memory is a big problem.
Yeah,
too.
memory is.
But in that case, you didn't mention about the DDR, only DRAM.
Yeah, actually, on this example, if this is the whole target region, your main bottleneck will be the main memory of your FPGA. Yeah. Like this is why I didn't write the target right above it, because well, optimizing this alone won't get you anywhere. That's right. Like the main issue you still have to solve is how do I get around the memory bottleneck? Yeah.
So my question is that you showed there some table of with separate items like VRAM or LUT and what is that?
You mean the usage of the main RAM of the FPGA?
So what do you mean that in the lows are all the benchmarks, right?
Yeah. So
and the columns are there. What do you mean that the LUT 0 point something and the VRAM is 0 point something? So
well, here it's the correlation of the predicted usage of these resources with the performance, and here it's the correlation between the predicted usage and the actual usage. We didn't predict the uses of the main memory because, well, it's not part of the actual IP kernel that we generated. The main memory is used basically on demand.
Okay. So that my next question is that why the prediction on the floating point or at the DSP is so bad?
That's a really good question, and we still have no answer.
Because I think that the DSP is some concrete
circuit. Absolutely. So you should be able to predict that.
So there maybe a street. I think that easily imagine that maybe the DSP part is a much better.
I agree. It should be really possible to predict that, but the large industry tools somehow fail.
That's very weird for me. Yeah. Okay. So currently you have no answer about that.
Yeah, I don't know. Well, we measured the correlation for VTIS, and they can't accurately predict the usage of the DSPs if you use floating point code.
Okay. Okay. Thank you very much.
Thank you. I think we have a question online from Mavit.
Yes. I have a question. Like, first, my understanding is that your work helps the end user to select the best HLS pragmas for FPGAs, right? That's the goal. Like you are. And in this context, how this methodology, is it scalable to all the pragmas? Like, if one thing is I can train this kind of prediction for limited pragmas very quickly, but if we would like to generalize, I don't know how much pragmas HLS has. Like OpenMP has a lot of pragmas for.
HLS has a lot of pragmas. Most of them are somewhat critical because they can actually break your code. They can make codes like syntactically or semantically wrong. So we focused on the pragmas that can't do that and that are, well, that actually change the compute side of things. There are some that like change memory bandwidth. We didn't focus on them because we will expect to find different correlations there. Does this answer your question?
Yeah, and one last, like, are you planning to use regression and decision tree kind of stuff? So are you considering machine learning as well, like neural net?
Yeah, the thing is, like, we don't have enough samples to use these really elaborate machine learning methods. We hope to be able to one day, but for now we stuck with the simple regression models because, well, taking one sample takes up 10 hours. So we had not like 100,000 samples to train like a deep neural network on that.
Okay, thank you very much.
All right, thank you. We have Steven. Can you go? And then we have one more in the room.
So my question is, so I think when you talk about performance, you're talking about runtime, right? But do you have data on frequency, the generated frequency? And is that something that's also, is it varying or is it reaching somewhere near what the board is capable of? Okay, we did our experiments with a fixed frequency and even a really low frequency, because lower frequency generally means that the synthesis takes shorter to run and you'll have less errors there. So we only compared like the degree of parallelism we achieved and how well we could predict it. Sure, you could also try to predict the maximum frequency you can run on that solution. Does this answer your question? Yes, thank you.
So regarding scalability, and excuse my ignorance on this field of FPGAs, but I wonder how does this work when you have multiple compilation units that each of those have multiple target regions?
You would generate one hardware block per, well, we have the pipeline. Where is it? Here. You would generate one IP kernel per target region, and then combine them all along one XC-bus normally to build your system with your multiple target regions. And our experiments focused on one target region per benchmark because, well, we didn't want to any interdependencies between.
So you would pass your mechanism over all the target regions then?
Exactly, yeah. You could apply our mechanism on every target region separately.
Separately?
Yeah.
So that means that you have to change the bit stream each time you execute the
can you speak up a little bit?
So maybe the main point I'm missing here is when you execute different target regions, you have to change the bit stream each time or you have a single bit stream?
Oh, you get one single bit stream for every that combines all target regions. Yes, you get multiple IP kernels, and they are all combined into one single bit stream.
So you have to be careful regarding which resources are available.
Exactly. Yeah.
All right. Just one last quick question before we get into the launch.
So first of all, I want to thank for a great talk. Just one question about the evaluation. What kind of real-world OpenMP program could benefit of using the FPGA?
Okay, that's a difficult question. We already got real-life benchmarks, for example, SpecExcel benchmarks, to run fast on the FPGA, but up until now, you'll need like a lot of manual tuning of, for example, these HLS pragmas. And we have already had the memory bottleneck. You have to get past that. So this is still manual tuning.
All right. Let's start the speaker.
Thank you.